A single lithium ion migrating between two crystalline hosts enables the portable electronics revolution. This process, known as intercalation, involves the reversible insertion of guest species into a solid lattice without significantly disrupting the host structure. Unlike lead-acid or nickel-cadmium systems involving phase transformation reactions, lithium-ion cells operate as rocking chair batteries. During discharge, lithium ions exit the anode and travel through an electrolyte to occupy vacant sites within the cathode lattice. Simultaneously, electrons flow through an external circuit to maintain charge neutrality. This movement is driven by the difference in chemical potential between the two electrodes. The integrity of the host framework determines the cycle life of the battery. If the lattice undergoes irreversible structural shifts during ion insertion, the capacity to store energy diminishes. Understanding these atomic scale movements explains why high-energy density storage maintains power over hundreds of cycles. Modern lithium-ion battery anodes predominantly utilize graphite due to its layered hexagonal structure. Graphene sheets are held together by weak van der Waals forces, creating spacious galleries for lithium ions to occupy. When the battery charges, lithium ions move into these spaces in a process called lithiation. This occurs in distinct steps known as staging, where the ions first fill every fourth layer, then every third, until reaching a fully saturated state where every layer contains lithium. At maximum capacity, the stoichiometry reaches 1 lithium atom for every 6 carbon atoms. This insertion causes the graphite to expand by approximately 10% along the perpendicular axis. High-quality graphite must exhibit high crystallinity to ensure low resistance and stable ion transport. Any impurities or structural defects can lead to irreversible lithium trapping, which reduces the total energy the battery can deliver in subsequent cycles.
Cathode materials must accommodate lithium ions at high electrochemical potentials to maximize cell voltage. Lithium cobalt oxide was the first commercial standard, featuring a layered structure where lithium sits between planes of cobalt and oxygen atoms. During charging, cobalt atoms oxidize from a 3+ to a 4+ state, releasing electrons to the external circuit while lithium ions extract into the electrolyte. To prevent the collapse of the layered framework, only about half of the lithium can be safely removed. Newer formulations like nickel-manganese cobalt oxide replace some cobalt to increase capacity and lower costs. Nickel provides high energy density, while manganese offers structural stability and cobalt prevents cation mixing. Other cathode types use spinel structures like lithium manganese oxide or olivine structures like lithium iron phosphate. These different crystal symmetries dictate the rate at which a battery can be charged and its overall safety profile during high-power operation. The electrolyte facilitates ion transport while acting as an electronic insulator to prevent internal short circuits. Aqueous solutions are unsuitable for lithium-ion batteries because the narrow electrochemical stability window of water leads to electrolysis at 1.23 volts. Instead, manufacturers use non-aqueous organic solvents, typically a mixture of cyclic carbonates like ethylene carbonate and linear carbonates like dimethyl carbonate. These solvents dissolve lithium salts, most commonly lithium hexafluorophosphate, to provide high ionic conductivity. Ethylene carbonate is necessary because it helps form a protective layer on the anode during the first charge cycle. The electrolyte must remain chemically stable in the presence of highly reactive lithium and stay liquid over a wide temperature range. High viscosity at low temperatures hinders ion movement, which explains why battery performance drops in cold environments. Additives are often included to suppress flammability or enhance the stability of the electrode interfaces.
During the initial charge cycle, the electrolyte decomposes on the anode surface to form the solid electrolyte interface. This thin layer is a complex mixture of organic and inorganic lithium compounds, including lithium carbonate and lithium fluoride. Although it consumes a small portion of the available lithium, this layer is necessary for battery operation. It acts as a passivation barrier that prevents further electrolyte reduction, while allowing lithium ions to pass through via a hopping mechanism. A stable interface protects the graphite from exfoliating and ensures a long cycle life. However, if the interface grows too thick, it increases internal resistance and slows down ion transport. Mechanical stress from the expansion and contraction of the anode can crack this layer, leading to more electrolyte consumption and capacity fade. Controlling the chemistry and morphology of this interface is a primary focus for improving battery longevity and fast charging capabilities. The energy a battery stores is determined by the Gibbs-free energy change of the overall chemical reaction. This is directly proportional to the voltage difference between the anode and the cathode. Lithium ions naturally move toward materials with a lower chemical potential. In a charged state, lithium is stored in the graphite anode, which has a chemical potential close to that of metallic lithium. The cathode consists of a transition metal oxide with a much lower chemical potential for lithium. When a circuit is closed, the system moves toward equilibrium, driving lithium ions to the cathode. The theoretical capacity of an electrode is calculated using Faraday's law, based on the number of moles of electrons transferred per gram of material. Actual voltage profiles during discharge reflect the varying energy states of the lithium ions as they occupy different sites within the host lattice. This produces the characteristic discharge curve seen in lithium-ion cells.
Ion transport within the battery involves both migration due to electric fields and diffusion driven by concentration gradients. Within the liquid electrolyte, lithium ions are solvated by solvent molecules, forming a coordination shell that increases their effective size. This shell must be shed as ions enter the narrow pores of the electrode and the crystal lattice of the active materials. The rate of diffusion is governed by Fick's laws and is highly dependent on the tortuosity of the porous electrode structure. Higher tortuosity increases the effective path length and reduces the rate at which the battery can be charged. In the solid phase, lithium ions move via vacancy or interstitial mechanisms. The speed of this movement determines the power density of the battery. If the charging rate exceeds the diffusion rate, lithium ions may accumulate on the anode surface instead of intercalating, leading to the formation of metallic lithium deposits known as plating. Battery aging occurs through multiple physical and chemical pathways. Each time lithium intercalates, the host lattice expands, causing mechanical strain that eventually leads to microcracking of the electrode particles. These cracks expose fresh surfaces to the electrolyte, causing additional solid electrolyte interface formation and further lithium loss. At the cathode, transition metal ions can dissolve into the electrolyte and migrate to the anode, where they disrupt the passivation layer. Furthermore, the electrolyte can undergo slow oxidation at high voltages, producing gases and acidic byproducts that corrode the current collectors. High temperatures accelerate these side reactions, leading to an exponential increase in the rate of capacity loss. Over-discharging a cell can cause the copper current collector to dissolve, which can then redeposit as dendrites during the next charge cycle. These dendrites pose a significant risk of internal short circuits, highlighting the necessity for precise electronic management of every cell.
Thermal runaway is a catastrophic failure mode initiated by an uncontrolled increase in temperature. It begins when the solid electrolyte interphase decomposes at approximately 80 degrees Celsius, exposing the reactive anode to the electrolyte. This exothermic reaction generates more heat, further raising the temperature. Around 130 degrees, the polymer separator melts and collapses, causing an internal short circuit between the anode and cathode. This releases the stored electrical energy as heat in a fraction of a second. At temperatures exceeding 200 degrees, the transition metal oxide cathode becomes unstable and releases oxygen gas. This oxygen reacts with the flammable organic electrolyte, fueling an intense fire that cannot be easily extinguished. Modern battery packs include safety features like ceramic-coated separators and pressure relief vents to mitigate these risks. However, the high energy density inherent to intercalation chemistry means that thermal management remains a primary engineering constraint for large-scale applications. To exceed current energy density limits, researchers are looking beyond traditional graphite and transition metal oxides. Silicon anodes offer a theoretical capacity 10 times higher than graphite, because each silicon atom can bond with nearly 4 lithium ions. However, silicon expands by 300% during lithiation, leading to rapid mechanical failure. Current solutions involve using silicon nanowires or carbon-silicon composites to accommodate this volume change. Another major shift is the development of solid-state batteries, which replace the liquid electrolyte with a solid ceramic or polymer conductor. This change eliminates flammability and potentially allows for the use of pure lithium metal anodes, which would drastically increase energy density. Lithium-sulfur and lithium-air chemistries are also under investigation for their even higher theoretical capacities, though they face challenges with conductivity and chemical stability. These advancements in intercalation and conversion chemistry continue to drive the evolution of energy storage for transportation and the electric grid.